Now, I am going to present you one of the most elegant method by which you can find out the various physical quantities associated with a simple harmonic motion and their relation and variation with respect to time. So far, we have tried to find out these physical quantities by using simple mathematics. They are fairly simple, but this method, called the reference circle method, is an even more simple way of doing the same things. Now, the reference circle method takes its cue from the intimate relation that exists between simple harmonic motion and circular motion. You know, the circular motion is periodic in nature, just like SHM, but there is a more intimate relation among the two, especially when the circular motion is uniform circular motion. That relation lays down the foundation of this elegant technique. Just see one of the examples. Suppose a particle is moving on a circle with angular velocity omega. So what is the time period for a full circle? We know from uniform circular motion it is 2 pi by omega. Now suppose the body is at A. When the body is at A and it is moving, you throw a light beam from the side, not from the top, from the side. It's moving like this. So you put a torch light at this side. Then you hold a cloth or a wall or an opaque barrier, and then you will see a shadow. It's common sense that the shadow of a circle, when it is sideways, will be a straight line. So you will find a straight line on the wall corresponding to the diameter of the circle. The length of the shadow will be d, the diameter of the circle. But follow the movement of this particle when it is here. When the particle is here and you throw a shadow, it will be a point. As it moves, the shadow of this point will move upward. When it moves to C, it will be at its maximum height. The shadow will be at point A. Then it comes from C to Z. It will come back from A to O, where it was when this particle was here. And then again the shadow will move downward. When the body is at this point, the shadow will be at the maximum bottom level, and then as it moves from here to here, it will go back from here to here. Now, what's new in it? The new thing is that, supposing this particle is at A, the length of O to A is nothing but the radius of the circle. Now, the radius of the circle, let us take the value A, which is the amplitude of a standard simple harmonic case. For example, the simple harmonic case can be a mass connected with a spring and making oscillatory motion around this point with amplitude A. We have conveniently drawn this circle with a radius A. Now, with a radius A, if this point is at OA, the shadow will be the projection of OA onto the wall. What is the projection of OA onto the wall when you throw the light? It is the vertical component of OA at position A, that is AX. If this is theta, AX is nothing but A sin theta. So the shadow will be at a height of A sin theta from the mean. This is the mean height, that is the reference height. So the shadow will be A sin theta. What will be at B when it gets an angle beta? It will be the projection of OB onto the wall, and that is OB sin beta. So the shadow of this point, as the point moves from A to B, will rise in height from this side to this side, corresponding to OB sin beta. Now, what is this sin theta? What is theta? In case of simple harmonic motion, theta is omega t. At time t, the angle traversed is omega t. So A sin theta is nothing but A sin omega t. what are we looking at is the shadow of this point is actually executing a simple harmonic motion around this point O, because it is exactly similar to our displacement function in the simple harmonic motion. For example, in this case, if we measure x from this point and t is equal to 0, x is what? A sin omega t, which is the vertical projection of point A onto the wall, the shadow of A on the wall. If the wall is vertical and we send the beam on the sides, it is nothing but the displacement function of a simple harmonic case like that of block spring. Now, what about the velocity and acceleration? In this case, in the case of position, we admit that there is a one-to-one correspondence. The shadow point moves exactly like that of a simple harmonic motion. In fact, it is a simple harmonic motion. The point in the circle moves in a circle. This point is going around the circle with angular velocity omega. While it goes around the circle with angular velocity omega, the shadow of the point across the wall is making a to and fro motion described by the equation sin omega t into something, and that is simple harmonic motion. Now, if you see the velocity at the point A, again the velocity is omega a. I have taken the counterclockwise direction omega a. You see, the vertical projection of omega a is again omega a cos omega t, which is the velocity in the case of simple harmonic motion. X is a sin omega t, v is omega a cos omega t. Similarly, the acceleration in this uniform circular motion is directed toward the center with omega square a. Again, its vertical component is minus omega square a sin theta, or theta is equal to omega t minus omega square a sin omega t. So, as far as displacement is concerned, and velocity is concerned, and acceleration is concerned, what we are seeing is a complete equivalence with a simple harmonic motion. The motion of the shadow in a circle, when the body executes a circle and from the side, the motion of the shadow is executing a simple harmonic motion. So, as the point in the circle covers a full time period t and a full circle, the shadow also makes a full time period t, just like the simple harmonic case here. So, for example, in this case and this case, when this body is here, it is the mean position. As it goes towards here, it goes here. That amplitude or the displacement goes on increasing, it becomes maximum here at A, and here it is A, and then it comes back to this position, it becomes 0, and here it is 0 as it returns back to mean position. So this position is say 0, this position is t by 4, this position is t by 2, and this position is 3t by 4, and this position is back to t. This is the case. Now, if we don't want to describe this as a sin omega t, suppose we want to describe it as a cos omega t, that is, we want to describe the motion of this block spring at t is equal to 0, x is equal to a, then how do we draw that reference circle? That is simple. The reference circles, instead of the vertical shadow or the vertical projection representing this, it will be the horizontal projection that will represent the displacement. The horizontal projection is a cos omega t. So you can do either way. You can tell that in the block spring system, the displacement is equal to vertical shadow. In this case, if you describe it by a sin omega t, if you describe it by a cos omega t, x is equal to a cos omega t, then you better take the horizontal shadow. Now, let's see some of the way in which an actual reference circle movement is panned across to make it similar to that of a simple harmonic motion. Let's see some physics applets so that we can get a better understanding, a pictorial feeling of this equivalence.